How do we relight and manipulate a scene based on geometry understanding, given only a 2D single image, without relying on additional sensor data? We propose a novel method called SIMBAR, which stands for Single Image-Based Scene Relighting. We present results from both SIMBAR in the wild and SIMBAR on AV scenes such as KITTI and BDD100K. SIMBAR is a modular pipeline with two distinct components. For the first component, geometry estimation. From a single 2D image, we predict a depth map using a pre-trained monocular depth estimation network, then warping a 2D planar sheet to generate a 3D scene mesh. After the 3D mesh reconstruction, a set of illumination buffers including normal map and reflectance map are rendered. For the second component, image relighting, given the source and target lighting parameters, the shadow maps are generated to indicate the presence and locations of the cast shadows. Shadow refinement networks R source and R target refines the source and target shadow maps respectively. These refined shadow maps and illumination buffers help the final relighting network R out generate the relit images. We compare our results with the prior multi-view scene relighting baseline MVR. MVR requires multiple viewpoints of a scene leveraging structure from motion and multi-view stereo. Such an approach fails at the video sequences captured by a stationary ego vehicle, resulting in hallucinated shadows in the relit frames, highlighted in red. In contrast, our method SIMBAR, with much fewer constraints on input data, provides significantly more realistic and geometrically consistent relighting results. To begin with, we used the MADAS V2. However, the generated depth map and the 3D mesh were often inaccurate and not fully representative of all objects in the scene, resulting in unrealistic relit outputs. On replacing MADAS V2 with DPT hybrid, a more refined and accurate description of the scene is obtained. Better geometry understanding contributes to more realistic relit images. Different levels of inverse depth thresholds can help scene mesh manipulation. For a high inverse depth threshold, a phantom wall gets formed. As a result, the top part of the pyramid has been mistakenly cut off by the depth boundary, attributing to the overshadowed scene with very dark sky. Our method utilizes low inverse depth threshold, which helps push the depth boundary further away so that the shadows of the objects located in the far depth range can also be rendered properly. Given the low-light desert scene, SIMBAR cleanly removes existing hard cast shadows of the rock in the foreground and realistically recasts geometric consistent shadows for the entire landscape. On the bottom, relit images for different lighting parameters are presented for a closer look. We additionally present two more examples: SIMBAR on the car racing field, SIMBAR on BDD100K tunnel scene. Looking into the predicted depth map and the 3D scene mesh of the bridge, we find parts located at far depth range have been mispredicted and misrendered. For the future, we hope to benchmark different depth estimation backbones for better scene understanding. Now our purpose is to validate the effectiveness of scene relighting as a useful data augmentation methodology for vision tasks. To validate the model performance on scene sync from real KITTI but on-scene lighting condition from virtual KITTI, we have trained the state-of-the-art multiple object detection tracking algorithm CenterTrack from scratch with the entire KITTI dataset, then augment the KITTI sequences 1, 2, and 6 with 4 different lighting and shadow variations. Looking at the inference visualization on the left, the baseline CenterTrack model K has the greatest number of false positives and false negatives. Our model trained with KITTI augmented with SIMBAR K plus S has overall the best performance. Quantitatively, we report that CenterTrack model trained on KITTI augmented with SIMBAR achieves the highest MOTA of 93.3%, a 9% relatively improvement over the baseline MOTA. This model has also achieved the MOTA of 94.1%, again an impressive 8.9 relative improvement over the baseline MOTA. Thank you for your time. For more details about our paper and the SIMBAR relit dataset, please visit our website, simbarv1.github.io.